Well, I'm going to talk about this document that talks about complex exponentials, signals, and the discrete Fourier transform. The first part is a background on the Fourier transform and how it works. The second part is on the fast Fourier transform, so that's what I'm going to talk about in this video. So the fast Fourier transform gives us a fast way of computing the discrete Fourier transform. And this is really essential because, as this paragraph describes here, and you can read this paragraph, that to do the Fourier transform directly takes a lot of computation. And the fast discrete Fourier transform really cuts it down tremendously. And fast Fourier transforms are used every day. Well, I shouldn't say every day, I should say every second, I should say every millisecond, because they're the basis of communication and the basis of audio. Any kind of digital audio will be using fast Fourier transforms. So let's go ahead and work through this, and I'll try to give you some more intuitive background on what's going on. All right. So we do have this pairing between the Fourier transform and the inverse Fourier transform. So this, I use this small s to denote the discrete Fourier transform of the big S. Now, since these are discrete, these are sequences, right? But we use discrete sequences to represent continuous time signals. So you should think about this as a signal in time, and these are components of frequency, right? So you've seen how you can break up a signal into frequencies. So this gives the frequency representation. The capital S's are giving the frequency amplitudes, and the small s's are giving the time amplitudes. Those are the ones that we observe. Now, because we're using complex exponentials, these amplitudes can be complex, and we'll see how that works out. And you'll see that there's going to be a very close relationship between these things and the complex roots of unity. All right, so the fact that the small s is this Fourier transform of the big S means that the big S is the inverse discrete Fourier transform of the small s. Now, in our method of finding a fast way of computing the discrete Fourier transform, we're going to start with this and work our way backwards. So you'll see how that works out. All right, now, this paragraph here gives a complexity calculation. It tells you how many multiplications and additions you would need to compute a conventional Fourier transform. This type of calculation is very important when you're studying algorithms. But I want to focus on the algorithm itself, so let's move on. Okay. All right, so it's interesting that this algorithm was first discovered 200 years ago and then rediscovered several times. Of course, Gauss was one of the greatest math geniuses of all time, and it's almost hard to find something that Gauss didn't at least discover partially during his time as a mathematician. So that may be a little bit of an exaggeration, but he had his fingers in many pies. All right, so let's look at a very simple example first. Now, we're going to start with the Fourier transform. So you think of these as the frequency components. And we're going to work our way backwards to the signal values. All right, so we'll just look at s at n equal 4. So if I want to find the inverse discrete Fourier transform, we have this familiar sum of the frequency components times these complex exponentials. Now, since this is inverse discrete Fourier transform, these are positive exponents. And here you have the summation index k and the output index j. So there are 4 big S's and 4 components of the inverse discrete Fourier transform, which are in fact little s0, little s1, little s2, little s3. So I actually probably should have written that here. Now I put the 4 over here because I didn't want to put it on this sum and have to rewrite it several times. So you should think of this as 4 times the inverse discrete Fourier transform. So this should be a familiar expression. Since it is Fourier transform of a signal length 4, you have the 4th roots of unity here. You have the 4 in the denominator. And you have your sum index k, and you're multiplying by j. And for j equals 0, 1, 2, 3, you get your outputs, which you should think of as small s0, small s1, small s2, small s3. Right? All right, so let's break out this sum. These are the individual terms when we group them. All right? Now, we can group them basically in pairs. So let's see how that works over here. Right? We really have the 4th roots of unity in the complex plane here, 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 and here. And we're grouping these two, and we're grouping these two. Right? Now, one thing to notice is that these two are the square roots of unity. And these two are the square roots of unity, but rotated. All right. Now, the square roots of unity are associated with a Fourier transform of length 2. So what we're going to do is kind of a divide and conquer. We're going to break up the Fourier transform of length 4 into 2 Fourier transforms of length 2. So this is just a purely algebraic operation. We're grouping them. Right, this is e to the 0 and e to the 2 pi ij over 2. So that's in fact, that's minus 1. Okay, so this pairing corresponds to the pairing I showed in this here, the horizontal pair and the vertical pair. Okay, so let's go and see how we do this. All right, so we are rewriting this horizontal and vertical pair as a pair of summations. Now, of course, here it's 4. I wrote it this way so that if you have a larger Fourier transform, you're going to use the same procedure, but just to show how it works in this simple case. All right. So here I just rewrote this sum using this summation notation. Right. There are 2 terms, so the summation index goes from 0 to 1. Right, and then here, because this is S2, I had to use 2 times my summation index. All right, so I'm doubling the summation index, and then that's what's getting me the square roots of unity rather than the cube roots of unity. So you can check out that this expression is just another way of writing this. So this is summing over evens, and this is summing over odds. Okay. Now you can recognize this as the inverse discrete Fourier transform of a 2-element signal. And this one also, because we pulled out this factor here. All right? So we have 2 2-element signals. Now, what the point that's made here is that that only works for j equals 0 and 1. That would give me my 2-element Fourier transform. But we also have j equals 2 and j equals 3. But it turns out that if I put j equals 2 in here, right, then that's going to give me e to the 2 pi I lj 2 over 2. That's the same thing as 2 pi I, right? That's going to be 2 pi I times an integer. So that's going to give me the same thing as if I had j equals 0, right? And same thing here. If I have j equals 2 here, that's going to be the same thing as if I had j equals 0. The only difference when I look at j equals 2 and j equals 3, I'm sorry, j equals 2 and j equals 3, the only difference is in this term, all right? So the way I deal with it down here is I say, okay, j equals 0 and j equals 1 is taken care of here. J equals 2 and j equals 3, well, I can replace the summation index here with j prime equals j minus 2. So j prime is 0 and 1, so we're still summing over 0 and 1. And then j will be j prime plus 2. Right? If I want to get j equals 2 and 3, I take j prime equals 0 and 1 and add 2. So I just replace the j here with j prime plus 2, and then the j prime is 0 and 1. Okay? And if I go through that, you can see that, in fact, you get the same thing as before. The only thing that changes is this term here. Instead of a plus, I have a minus. Now, this is actually called a butterfly. So this one goes up, this one goes down. But otherwise, the terms are the same. So it's like two wings of a butterfly. That's kind of a fanciful analogy, but you'll see later on how that works out, how it makes sense to call it a butterfly. All right? So we summarize that when j is in 0 and 1, we can get the inverse discrete Fourier transform of this 4-component signal as the sum of two component discrete Fourier transforms. And same here, and you have the same two discrete two-component Fourier transforms, but instead of a plus, you have a minus. Now, to compute a 4-component discrete Fourier transform directly, or I should say inverse discrete Fourier transform, to compute that directly takes quite a bit of computation, a lot more than to compute a 2-component. So, and computing two-component Fourier transforms is a lot less computation than computing one 4-component inverse discrete Fourier transform. All right. So we've saved a lot of time. All right. So that's the basic trick that we're going to apply again and again. Now we're looking at inverse discrete Fourier transform. But just bear with me. What we're going to do is do it this way, and then we're going to work our way backwards. All right? That's what we're going to do. All right? So, and these factors of 4 and factors of 2, don't get messed up with that. You can always just add that. So, and I should have written a dot there or something to show that it's 4 times this inverse discrete Fourier transform. Now, where are we going with this? I mentioned that we're trying to compute the DFT and not the IDFT. So why are we talking about the IDFT? Well, this IDFT is my original signal. Notice that here, this is the original signal. I've expressed it in terms of smaller IDFTs. What I actually want to go is to compute these smaller IDFTs from my original signal. So I want to get an expression for these smaller IDFTs from the DFTs of the 4-component signals. Because, in fact, this IDFT is what I know. This IDFT of the signal components is my original signal. This IDFT here is small s0, small s1, small s2, small s3. Let me just emphasize that. I'm going to grab this and put in my here. So let's insert that. Okay. All right. So this here is actually equal to 4 times S0, S1, S2, S3. Okay? So this is what I know. This is what I'm starting out with. And I want to get these two. So I'm going to invert this relation. This is a very easy relation to invert. I'm going to solve for these two in terms of the original, right? This is the same thing. This is going to be the first two components, S0 and S1, and this is going to be the second two components, okay? The j plus 2 here, right? Because j goes from 0 to 1. So I'm going to invert this relation, and that's what we have here. Oh, sorry. Let's get there. These 2-component IFDFTs come from my original 4-component IDFTs. All right? So let me reemphasize that this equation gives me a way of computing these 2-component IDFTs from these IFTs, which are the original S's. Okay? All right. Now, I'm going to repeat this process. You see here I had a 4-component IFDFT, and here I have a 2-component, and I should be able to do the same thing, the same type of equation I did here with the 2 components. Let's see how that works out. Okay? I'm just going to do some analogy here, some analogous reasoning, and we can verify it on the next page. So let me grab both of these. Okay. All right. So let's see if I can do the same thing with these two that I did with this. All right. So instead of the for component, let me start with the first one. Okay. All right. So now instead of for, we have 2. So I'm going to say 2 IDFT of S0, S1, S2. And I'm going to take the jth component. Now, of course, here j is just going to be 0 and 1. Okay. Now here we're going to have, instead of 2, we're going to have a 1 now, because we're going down 1. So this is just going to be IDFT. Okay. Now here we took S0 and S2, which were the evens. So here is this just going to be S0. And then here, and you could do this computation in detail and see how it works. Do the same computation we did before, but it is very analogous. This is going to be plus 1. And then this is going to be e to the 2 pi I j. Now, again, we're going from 4 to 2, so that's going to be a 2. And this is going to be I dft. And in this case, this is going to be the odds. These were the odds. Now, in this case, the odd is S2. Okay, now let me clarify here. We were looking at this first equation, and remember, when each equation that we started with broke up into 2 equations. So here, when we had 4 component, this was j equals 0 and 1. This would just be for j equals 0. And the j equals 1 is going to be different. Okay, so that's going to be the second equation. Here, I'm going to do an analogy of this equation. This will be 2 IDFT S0, S2, and this is going to be, again, this j plus 1 equals IDFT of S0, and then this is going to be minus e 2 pi I j over 2 now. This is going to be IDFT of S2. All right. So this gives me a way to express this IDFT in terms of 2 other IFTs. And then we're going to have the same thing where S0 goes to S1 and S2 goes to S3. Same equation. Okay. And that's what's on the next page. But what we want to do, in fact, is what our goal is to find this here. The IDFT of S0 is 1 point IDFT. It's just the same thing. IDFT of F0 is just S0. Okay. IDFT of S2 is S2. So if I invert this equation here, then I'll be able to get S0 and S2 from these IDFTs. And I'll be able to get S1 and S3 from the IDFTs here. All right? So let's look at the second page and see how that works out. It's not going down for me. Let's try again. Okay. So you got 4 equations here. So the S0, S2, S1, S3. Okay. Right now, so what's the point here? In order to compute the capital S's, what you do is you put in the small s's in for this IDFT, right? Okay. The small s's is going to go here. So IDFT S0, S1, S2, S3, J is just small s of J. Okay. And so we have this. So when we have these expressions down here, which is what I'm going to be using, I can get this 2-point FFT from this. This here is just going to be small s of j, and this is small s of j plus 2. Okay, and same thing here. Okay, so you're going to start out with the small s's, plug them in for these 4-point ISDFTs, and these intermediate quantities you can keep the same. All right. So you're going to use these what you have here to compute these intermediate quantities. Then you're going to use these intermediate quantities to compute the final quantities. All right. So that's how it works. Okay? If you look at this one here, the DFT of 1, 0, 0, 0, that means that S0 is 1, the other S's are 0. So that means up here, when you do this equation here, you're only going to have a term when J equals 0. All the other terms are going to be 0. Okay? So that's how it works. Give it a try.